Hi everybody, welcome to Tuesday. Today we will be going over Newton's second law and talking a little bit about what kinds of forces change an object's motion. These are the first three that I have pulled up here. Friction changes an object's motion, air resistance, and gravity. What is friction? Friction is resistance to motion when two objects are in contact with each other. The resistance between like a tire and the road. Air resistance would be the resistance on an object feels when traveling through the air. I guess if you kind of think of a car, it's how fast the air is pushing against you. So that would be the air resistance on a car as you're moving forward or backward. And gravity is the attraction two objects have on one another. The force of gravity pulls us towards Earth. So gravity is what keeps your car on the ground. Friction depends on three factors. So the rougher the surface, the greater the friction. Those little tiny bumps are called micro welds on any two things that are touching. And the greater the force pushing the two objects together, the greater the friction. And the greater the surface area of the two objects touching, the greater the friction. So the rougher the surface, the greater the force, and the greater the surface area. The rougher the surface is how bumpy it is. The greater the force is basically just how much force is being pushed against something. And the greater the surface area is just how much of an object is actually touching the area of the object it's being pushed against or over. We got three types of friction, basically. We have static friction, which is the force between two surfaces that are not moving past each other. So that would just be a block sitting on a table. Sliding friction, it's the force between the two surfaces that are sliding past each other. So the block is sliding on the table. And rolling friction would be a force between a rolling object and the surface it rolls on. Just a rolling motion. We all know what rolling is. Air resistance. This is friction in the air. So it is determined by speed. The greater the speed, the greater the resistance. Size. The larger the object, the greater the resistance. And shape. The flatter the object, the greater the resistance. So a flat-nosed, that's why airplanes don't have flat noses, because that would be a lot of air resistance that it would be coming up against. If you think about airplanes, you can kind of think about this. They go fast because they're big and they all have pointy noses. And then we'll move on to the law of universal gravitation. It's any two masses that exert an attractive force on each other. So it depends on mass. The greater the mass, the greater the gravitational attraction. So that is what you will put down. And distance. The lower the distance, the greater the gravitational attraction. There's your example. The attraction to Earth that pulls an object in the air downward. Gravity just basically pulling everything towards the ground, everything down. And it's why we're getting pulled all towards the Earth all the time and we don't go floating off into space. This force causes all falling objects to have an acceleration due to gravity of 9.8 meters per second squared. 9.8 meters second per squared is an important number, and it is the acceleration due to gravity always. So write that down somewhere because you will definitely use it later. And it doesn't matter how much mass something has, and that's also ignoring air resistance. Of course, air resistance would change some of that. Terminal velocity. What is terminal velocity? It's the maximum velocity a falling object will reach. And if we think of what was velocity, it's the speed in a direction, right? So it's the maximum velocity this guy's going to reach as he, falls towards the Earth. It occurs when the force of gravity and the air resistance become balanced. So the force of gravity pulls you down and the force of air resistance kind of opposes that, so it pushes you up. And at a net force of 0, there will be no acceleration, and that will be your terminal velocity. So it'll be a constant speed. And for humans, it's 55 miles per second. meters per second, or 118 miles per hour. That's how fast we fall towards Earth at terminal velocity. All right, so now we're just going to move on to Newton's second law of motion, how do motion and force relate. Newton's second law is a net force acting on an object causes the object to accelerate in the direction of the force. The little example over here is a croquet, because we all play croquet all the time. The croquet mallet hits the little croquet ball thing, and the ball is going to go in the direction that the mallet hits it with a certain amount of force, right? Pool, even basketball, when you make a pass, you throw it towards the basket. There's lots of examples. The greater the mass, the greater the force needed to accelerate it. So the bigger that little croquet ball gets, the more force you need to get that ball to move across the ground. And the greater the net force, the greater the acceleration. And the harder you hit it, so the more force you put into that swing, this is just going to accelerate faster. And it will accelerate in the direction of the net force the mallet applies. Okay, so let's summarize it as an equation. I'm not sure, but many of you have probably seen force equals F equals ma, which is just force measured in newtons, mass measured in kilograms, and acceleration measured in meters per second squared. So force equals the mass times the acceleration. So here's our first example for today. You are pushing a friend on a sled. You push with a force of 40 newtons. Your friend and the sled together have a mass of 80 kilograms. Ignoring friction, what is the acceleration of your friend on the sled? So you don't have to worry about any friction here. It's a frictionless surface. So what do we know? We know that the force equals 40 newtons. We know that the mass equals 80 kilograms. And we know that we want to figure out what the acceleration is, right? And we also have this little formula, F equals ma, but we need to solve for a, so let's figure that out. Divide both sides by mass. And there's our formula. Acceleration equals force divided by mass. So let's plug that in. So 40 newtons divided by 80 kilograms. The acceleration is going to be 0.5 meters per second squared. You can feel free to write this little formula down, then you won't have to solve for it later. Now we're going to talk about weight. Weight and mass are not the same thing. Weight actually measures the force of gravity on an object. So because it's a force, you can always calculate weight using force equals mass times acceleration. And when finding weight, acceleration due to gravity is always going to be used. So it's always going to be 9.8 meters per second if you're trying to figure out the weight of an object. So example number 2, here's our example. I don't think you have this on your sheet, so write it somewhere in the corners. Turn your paper sideways. Find the weight of a suitcase that has a mass of 42 kilograms. What do we know? That mass equals 42 kilograms. We're looking for weight, so we know A equals 9.8 meters per second squared. And we're trying to find force. Formula, force equals mass times acceleration. So force equals mass times acceleration, or 42 times 9.8, or 411.6 newtons. So that suitcase weighs 411.6 newtons. When we think of weight, we usually think of it in pounds, and that's a completely different formula. To keep it simple and to keep it relevant to Newton's law, we'll be measuring weight in newtons. If you knew your mass, so if you knew your mass, like how many kilograms you were, you could figure out how many newtons you weighed. All right, so what is the difference between weight versus mass? Because we say, I weigh blank kilograms or I weigh blank pounds, but that's not exactly the same thing. Mass is the amount of matter in an object, and weight equals the force of gravity on an object. So it can change based on location. So the further from Earth you are, the lower your weight. If you're on the moon, your weight would be 1/6 of what it is now. So if you weighed 100 pounds, well, you would weigh 16.66666 pounds. And if you could be on another planet, your weight would change based on the gravity of that planet, because the gravity changes from planet to planet. So on Jupiter, your weight would be over twice as much as it is now. So if you weighed 100 pounds, on Jupiter, you weigh over 200 pounds because of the force of gravity of Jupiter. Okay, so now we're going to practice. So we'll go ahead and shut this particular video off. Get your notes done. When you're done, please fill out the feedback form. And we're going to watch the next video right now, which will be the video sort of introducing the practice sheet for today. And then I also want you all just to know that starting on Friday, actually, you will be doing a unit on the solar system. So you'll kind of be getting away a little bit from physics. All right.